Let me just recall back the definition of a ring. Let take R to be a non-empty set equipped with two binary operations plus and multiplication. Then the algebraic structure R plus dot is called a ring if the following axioms hold. Number one is that R under the binary operation plus should be an abelian group. Is an abelian group. That means it must satisfy all the group axioms. The first one is the associativity, that is A plus B plus of C, that is A plus B plus C should be the same as A plus B plus C for every A, B, C belong to R. And number two is existence of additive identity, and that is there must exist an identity element in R such that, say 0, such that 0 plus A should be same as A plus 0, which is called A. And existence of inverse, additive inverse. For every A belongs to R, there must exist minus A belong to R such that A plus with minus A, this should be equal to the additive identity element 0. So this R and the plus must satisfy those three properties, and an abelian, to be abelian, it must satisfy the condition that A plus B should be the same as B plus A for every A, B belong to R. Number two axiom is this one: multiplication dot in R satisfied associative law. That is, under multiplication, A dot B plus B dot C should be the same as A dot B dot C for every A, B, C belong to R. And the last one is the distributive law holds in R. That is, A dot B plus C should be the same as A dot B plus A dot C, and this is called as the left distributive law. And number two is A plus B dot C should be A dot C plus B dot C, and this is called as the right distributive law. So now here let us come to this next definition. Let R and the plus and dot be a ring. That means the algebraic structure, this one is a ring. It means that it satisfies all these properties. If the binary operation dot now satisfy the commutative property, that is A into B is same as B into A for every A, B belongs to R. That is, under multiplication, A, B must be equal to B, A. Then in that case, it will be called as a commutative ring. Then in this case, R and the plus and dot is called a commutative ring. So R and the plus and dot will be called as a commutative ring if it satisfies the property A into B is B into A for every A, B belongs to R. Now next, let us define this definition. Let R under binary operation plus and dot be a ring if there exists an element 1 belong to R such that 1 into A, that is under the binary operation dot, 1 into A should be the same as A into 1, which is equal to A for every A belongs to R. Then this one is called as the multiplicative identity or the unity element in R. And in case if the multiplicative identity element exists, then in that case R is called a ring with multiplicative identity. So let me give you an example of a ring with multiplicative identity 1. If you take the ring of integers and addition and multiplication, where set is this one, contains 0, plus or minus 1, plus or minus 2, and so on. This one is a ring with multiplicative identity 1. Since for every m belong to set, that means for any integer m belong to set, it can be 0, it can be 1, it can be minus 1, it can be 2, minus 3, and so on. 1 into m is always equal to m into 1, which is equal to m. So therefore, the ring of integers and the addition and multiplication, the usual addition and multiplication is a ring with multiplicative identity. However, if I take this one, 2 set and the plus and dot, this algebraic structure satisfy all the ring axioms, where 2 set contain only this even integer 0, plus or minus 2, plus or minus 4, and so on. Now since this 2 set under the usual addition and multiplication satisfy all the ring axioms, so therefore it is a ring. But it is a ring without multiplicative identity 1. Why? Because 1 does not belong to 2 set. And we know that 1 is the only element which satisfy the condition that 1 into any element of 2 set will be equal to that element of 2 set. So therefore this is a ring without multiplicative identity 1. Number 3, you can take this one, M2 over R. That means a set of 2 cross 2 matrices form X, Y, U, V, such that X, Y, U, V belongs to R. They are real numbers. So this, we know that this is a ring. I've given you the explanation on this one, how this M2 over R satisfy all the ring axioms in the last lecture. So you just go through that one. So M2 R under the addition of matrices and multiplication of matrices, this is a ring. But now this is not commutative. It is non-commutative. But it is a ring with multiplicative identity, because the multiplicative identity of this ring is this one, 1 0 0 1. So therefore this is a ring with multiplicative identity, but it is not commutative or non-commutative or a non-commutative ring. Why? Because if you take A is equal to this one, say 1 0 1 0, and B is equal to 0 0 1 1, then what is AB? AB is equal to, if you multiply A into B using the matrix multiplication, then this one you'll get as 0 1 0 1 again, and BA is equal to 1 1 0 0. Now you can see that these two matrices are not the same. Therefore AB is not equal to BA. That means this is a ring which is not commutative, or it is a non-commutative ring. Now next, let me give you an example of number 4. If I take M2 over 2 set, that means this consists of the 2 cross 2 matrices to form X, Y, U, V again, such that X, Y, U, V belong to 2 set. That means the entries here are even integers. That means one will not be an element here. So again we know that this one, if I take the elements, say A is equal to 2 0 2 0 and B is equal to 0 3 0 0 minus 2, then AB will give you a different value and BA also will be different. So therefore again it is not commutative, but it is also a ring without identity. Why? Because 1 0 0 1 does not belong to M2 over 2 set. So this is an example of a non-commutative ring without identity, and this one is a non-commutative ring but with a multiplicative identity 1 0 0 1 exists in M2 over R. So these are the few examples of the ring with which is commutative and non-commutative, and also a ring with identity and multiplicative identity. Now next, let me define this definition. Let R and the plus and dot be a ring if there exists an element A, B belong to R such that the product A into B becomes 0 or B into A becomes 0, but neither A is equal to 0 nor B is equal to 0, then in this case we call A and B are called the divisor of 0. 0 or the 0 divisor. So we take R to be a ring under the addition binary operation plus and dot, and if you can find an element A and B belong to R satisfying the condition that their product becomes 0, AB 0 or BA is equal to 0, but none of them is equal to 0, then in that case A and B are called the divisor of 0 or the 0 divisor. For example, you can take the ring. Example, consider this ring R is equal to M2 over set of real numbers. Now if you take the matrices, A is equal to 1 0 0 0 and B is equal to 0 0 1 1. This belong to M2 over R. Similarly, this also belong to M2 over R. But what is AB? Now none of them is equal to the 0 matrix, because a 0 matrix, the 2 cross 2 0 matrix is denoted by 0, which consists of all the in which all the entries are 0 0 0 0 0. But neither A nor B in this case is equal to the 0 matrix. But if you take the product of these two, then it will give you 0 0 0 0. So you can see that A and B are neither A nor B is equal to 0, but their product becomes 0. So these are A and B are called as the zero divisor of this ring M2 over R. Now next, a ring R is said to be without zero divisor if for any AB belongs to R, if the product AB is equal to 0, it will imply that either A is equal to 0 or B is equal to 0. That means whenever the product AB is equal to 0, then at least one of the element must be equal to 0. Then in that case, a ring R is said to be without zero divisor. And a simple example for this ring without zero divisor is the ring of integers. So this is an example of a ring without zero divisor. Because we know that the product of two integers, non-zero integers, can never be equal to 0. However, if the product is equal to 0, that means at least one of the integer must be equal to the 0 element. So therefore, the ring of integers and addition and multiplication is an example for ring without zero divisor, but the ring of 2 cross 2 matrices over the set of real numbers is a ring with zero divisor, because we can, since there exists an element A and B which are not equal to 0, but their product becomes 0. So I hope it is clear now with the definition of the zero divisor.